Okay, hello everybody. Sorry I'm a little late. A little trouble making Zoom behave. Uh, Momentarily, this will be full screen and we can go, or maybe not, or not. Interesting. Okay, well, I'm glad we're recording this riveting footage of me staring at the screen. I think that worked. There we go. So, are there any questions before we get going? I remember how to do this. I put my little face over here, and then that should show up just fine. So, seriously, are there any questions? Everybody ready to go? Put it on the chat. Sorry, I'm a little late because I had trouble making Zoom behave. All right, let us go. Okay, so let capital I be the principal of ideal of R generated by x squared plus 1. Find some polynomial in I that the degree of f of x is greater than or equal to 3. So I, oh my goodness. Come on, computer. I is the set of all polynomial multiples of the generator x squared plus I. That's the definition of the principal ideal generated by x squared plus I. So that's one thing, So not only do you need to know the definition of ideal, but you need to be able to you need to know the definition of principal ideal because all the really cool ideals that we deal with are a principal. And so since I is right is a principal ideal generated by x squared plus 1, well, any multiple of x squared plus 1 is in I. So if I take x squared times x squared plus 1, that's in I. So f of x equals x to the fourth plus x squared is an adequate answer. So everybody good so far? You lucky folks who are here and have working sound and have hung out, you're representing everybody else. So everybody good with that answer? Okie doke. And everybody can hear me okay, right? Say yes if you can hear me okay. Oh, okay, very good. All right. I think you two might be the only folks left here. Oh no, Abisha's back. Okay, so right. So let F128 be the field is the field of order 128, where alpha is a root of x to the seventh plus x cubed plus 1. Let beta be alpha cubed plus alpha squared plus 1, and let gamma be alpha to the fourth plus a. So fill in the blanks. An element of F128 is in reduced forms of polynomial in the variable alpha. So I think I would accept. Let's try that again. I would accept x, but alpha is a better answer. Of degree at most 6, because as we'll see in a minute, the point of having that alpha to the seventh equals alpha cubed plus 1 is that it can reduce any polynomial of that degree or of degree 7 or higher to something of lower degree, and so you eventually get something of degree 6 or lower. All right, so find a reduced representative for beta gamma. So beta gamma equals alpha cubed plus alpha squared. I don't know why my computer's going so slowly, other than my computer is terrible. Oh well. Alpha to the fourth plus alpha it is kind of fun to watch the writing catch up with my finger. Anyway, so first of all, multiplying that out, we get alpha to the 7th plus alpha to the 4th plus alpha to the 6th plus alpha cubed plus alpha to the 4th plus alpha. And so those things cancel out. Let's see, 7, 7, 4, 6, 7, 4, 6, 3, 4, 1. Okay, so that's good so far. But now, so that's correct, but it's not reduced yet because I have to replace alpha to the 7th with alpha cubed plus 1 in order to get a truly reduced representative. And then we have yet more cancellation. And so the final answer is going to be alpha to the 6th plus alpha plus 1. Okay, so is number 2 okay? Okay, next. Let F16 be a field of order 16. Give an example of a ring of order 16 that is not isomorphic to F16. Briefly justify your answer. Okay. I should have said it ring R, but so let R be Z mod 16. So because one of the big lessons that you want to get out of chapter 7 is why do we go through all this complicated rigmarole of looking like quotient rings of rings of polynomial mod irreducibles? Why do we have to do all that business? It's because the field of order 16 is not Z mod 16. So the first thing I think like, oh no, that's right. Z mod 16 is not a field, and so and then you want to have to. So that's a big chunk. Excuse me, a big chunk of what you need. But to justify that this is not isomorphic to F16, 4 times 4 equals 0 in Z mod 16. And a field can't have 0 divisors, something that's proven in the book. 0 divisors. At least the slowness of this writing is slowing me down. A field can't have 0 divisors, which means that R is not isomorphic to F16. Yeah, and that in fact, not only is that sort of an important fact to know, but this is actually kind of the standard way to prove that fact. That if your modulus has sort of non-trivial factors, then that gives you 0 divisors, and that's why you don't get a field. So number 3, okay. Easy peasy. There we go. Sure. Okay. Next, number 4. Let F2048 be the field of order 2048, and let F2048 times be the multiplicative group of F2048. So note that 2048 is equal to 2 to the 11th, and 2047, ooh, tricky, is equal to 23 times 89, both of which are prime. And so what are the possible orders of elements? Try that again. Orders of elements of the multiplicative group of F2048. Well, they're their divisors of 2047, which since 2047 just happens to be divisible by exactly 2 primes, they're 1, 23, 89, and of course the number itself, 2047. So I mean, it's maybe not so easy to figure out that uh, that period then did not improve things. To figure out that the divisors of 2047 are exactly those numbers, but if you at least wrote, it's just the divisors of 2047, whatever those are, then that's something. Okay, sorry. Nothing like putting the hand in the camera to make my video more interesting, huh? Okay, so yeah, so that's the answer to part A. Part B, for a given alpha, in the multiplicative group, what's the smallest set of powers that we need to compute to see if alpha is primitive? Uh, uh, well, here's one possible answer. So if alpha to the 1 and alpha to the 23 and alpha to the 89 are not equal to 1, then the order of alpha will not be equal to 1, 23, or 89, which will then imply that the order of alpha is 2047. And this is the sort of thing we did in class. Sort of what do we have? What exactly do we have to do to figure out that a particular element is primitive? Well, you kind of go up to the all you have to do is compute the powers up to the largest divisor of q minus 1. That's not q minus 1 itself. So if none of those hit, then the order's got to be q minus 1, which then implies that alpha is primitive. So the answer is alpha to the 1, alpha to the 23rd, and alpha to the 89. I suppose if you had some magic way of computing alpha to the 23rd, you don't really need to compute alpha to the 1, because if alpha to the 1 is 1, then so is alpha to the 23rd. But okay, good enough. Questions. I thought I saw a question in the chat. So how many points off for including alpha to the 2047? Some. I don't remember how many points. Definitely some, because the point of the question, because as you sort of saw on the homework, is that you don't actually have to compute alpha to the 2040. Well, actually, let me make a note in green, because it's not really part of the answer to the problem. But so note, and B is a fancy Latinish way of saying nota bene. Alpha to the 2047 is always equal to 1. So there's never a need to compute it. Yeah, that's a theorem. That's you can look at that as the order part of the theorem, or it's actually the magic polynomial says that alpha anything to the 2047 is going to be equal to 1. Okay. Any other questions about this? Okie doke. That's well, let me ask, is number 4 okay? Hey, Abisha, you can hear me now. Okay, great. Okay, next. Let F64 be the field of order 64, which is 2 to the 6th. And let F64 times be the multiplicative group of F64. So let alpha be a primitive element of F64. What is the order of alpha? Briefly explain your answer. I don't know what kind of what was I thinking when I said that? There's not much of an explanation to give. The answer is the order of alpha equals, I guess the following thing is actually a sufficient explanation. It's the order of the field minus 1, which is 63. So that's A. And now B. So exactly one of the following is true. Either there exists an element of order 3 or there exists an element of order 4. And the one that is true is going to be that there's an element of order 3. So I circled the true statement, and this is not part of the answer, but worth mentioning that this is false because 4 doesn't divide 63. Right, so the orders of elements of the multiplicative group of a finite field are exactly the divisors of q minus 1. It's another one of the strange minus ones that shows up in chapter 7 or 8 that are kind of annoying. Anyway, so circle the true statement. Explain how to find such a statement of in terms of alpha. Well, if beta equals alpha to the 21, and you want alpha to the 21 because basically you want to divide the order of alpha by 21 to get to 3. And then the order of beta will be equal to 63 divided by the GCD of 21 and 63, which is in fact 3 because 21 divides 63. So yeah, so that's how you find beta. And there was a question in the chat. Yeah, we don't need to explain. Yes, we do. But yeah, we do need to explain, but it's a very short explanation. So yeah, oh yeah, that's right. Look at it. Look at this. I did learn something over pandemic. Like I learned to use this thing. So right. So this, yeah, except it only really works for the mouse. This is actually an explanation of why the order of alpha equals 63. It's because it's 64 minus 1. It's not much of an explanation, but it's actually the explanation that you need. And this explains why the order of beta is 3. So Venom, does that make sense? That those were the explanations that I was looking for? Yeah, so I take it number 5 is okay. Oops, number 5, okay. Number percent sign, okay. Yeah, okay. Good. All right, number 6. Let alpha be a primitive element of F256. And so, yeah, here's that q minus 1 again. So the order of alpha is 1 less 255, which means that alpha to the 255 is 1. Good way to remember it. So find the minimal polynomial m of x of alpha to the 5th over f2 expressed as a product, well, in the usual way. So the orbit number 5 is going to be alpha to the 5th. I squaring it alpha to the 10th. Boy, I hope I can do this arithmetic correctly on camera. Alpha to the 20th, alpha to the 40th, alpha to the 80th. Okay, alpha to the 160. 320. 320 minus 255 is 65. Yeah, let me double check that. That's probably useful to, so 320 minus 255. Yeah, that's 65. So that's what goes over there. And so great. And then alpha to the 130. And then, oh yeah, and then so here's a sort of way to sort of check on things. 256 is 2 to the 8th. And so the orbits, the Frobenius orbits of elements in F256 times, the multiplicative group of F256, are all those orbits are going to have length dividing 8. And so, we got to 7. So I got to 8. Well, that better stop. So yeah, so we got to 9. We know we messed up somewhere, but that's it. And so and again, so that's okay. And so yeah, because 260 mod 255 is 5. So we circle back around. And so m of x, or if you like m sub 5, is going to be equal to x minus alpha to the 5 times x minus alpha to the 10 times x minus alpha to the 20th. I'm sure many of you at this juncture are asking if you can just abbreviate this. And I suppose if you abbreviated this in some way that made it clear what you were doing, I'd probably let it go. But on the other hand, why bother to abbreviate? Because it takes more time to think about how to abbreviate it than it does to actually write it all out. Anyway, there it is. So there's m of x. So yeah, so that's how you find the minimal polynomial. Questions about that guy? Yeah, these are taking a little longer now. Only 2 more to go, but they're a little bit longer now. So is number 6 okay? Anybody watching this, you should thank the folks who are here for ably representing your class. Okay, so right. In F2 bracket X, we have these following facts. Okay, so those are given. And so now, oh yeah, so this is right. So we're going to find the inverse of something. And so that's M. So there's M right there. And so beta is alpha cubed plus alpha. And so our B is over here. And this is also B. Okay, so and this is m equals 0 mod x to the 5th plus x squared plus 1. So we're going to find the multiplicative inverse of beta, and we do that using Euclidean reduction in the following way. So the first, yeah, I don't think I've ever done this with like equation numbers, star 1, star 2, and star 3. So from star 1, we see that 0, because m is really equal to 0, is equal to x squared plus 1 times beta. Oops. I don't really want x squared plus 1. I think I'm going to be a little fussy here. If you write x squared, it's fine. But I'm going to be a little fussy and write alpha squared. So it's alpha squared plus 1 and plus alpha squared plus alpha plus 1. And so if we rewrite and solve for the remainder, we get alpha squared plus alpha plus 1 is equal to alpha squared plus 1 times beta, because thank God in the money-making character in the moneymaker characteristic 2, plus is equal to minus. So I hope everybody's good so far. We get to start 2. So I think no questions so far. Okay, star 2 says that this time let me be a little bit more careful about this. Star 2 sort of solving for the or a little more efficient about this. Star 2 solving for the remainder says that alpha plus 1 is equal to beta minus, which is really plus, x plus 1 times, oh, sorry. You can write x, it's fine. Alpha plus 1 times alpha squared plus alpha plus 1. Yeah, that's right. Right, so because I moved this stuff over here, over to the other side. and rewrote in terms of alpha. And so, but we know from before that well, here's the alpha plus 1 that stays, and we know that alpha squared plus alpha plus 1 is equal to alpha plus 1, alpha squared plus 1 times beta, right? So remember that, and that came from the previous stuff. And so, resuming, you see that this is equal to beta plus alpha cubed plus alpha squared plus alpha plus 1 times beta, and which is equal to alpha cubed plus alpha squared plus alpha times beta. Because remember, as they say in pre-calculus, or just or like algebra 2 or algebra 1, really, remember there's like a little invisible 1 over here, right? Beta is equal to 1 times beta, and so this 1 over here cancels out this 1 over here, and we're left with alpha cubed plus alpha squared plus beta. So is everybody good with step 2? Any questions about step 2? All right, step 3. So step 3 says, if you look at step 3, here's a question about step 2. Oh, all good. Okay. So if you look at star 3 over here, this says that pushing this stuff over to the other side, we see that 1 is equal to alpha times, it was alpha plus 1? Yeah. Alpha plus 1 plus alpha squared plus alpha plus 1. It occurs to me that, even though I'm going to go back up and check that I copied this correctly, which I did, you can just actually, you don't really need to copy it correctly. You just need to check that what you have over here is true. And yes, that's true. This is going to be alpha squared plus alpha. And if I add alpha squared plus alpha plus 1, I get 1. Great. And so fortunately, we have this. We've already solved for these other things already. So alpha plus 1, we just said, was alpha cubed plus alpha squared plus alpha times beta. And then alpha squared plus alpha plus 1 was alpha squared plus 1 times beta. So just again, so that was copied over here, and this was copied over there. So just to be really careful and multiply get all the stuff, cross all my I's and dot all my T's. That joke. Alpha cubed plus alpha to the 4th plus alpha cubed plus alpha squared beta plus alpha squared plus 1 times beta. And so we see that 1 is equal to alpha to the 4th plus alpha cubed plus 1 times beta, which means that beta inverse, whoa, that was wild, beta inverse is equal to alpha to the 4th plus alpha cubed plus 1. Phew. Okay. Let me pull back and let everybody, including the folks at home, see this in its full glory. Fit to size, that's right. There we go. Okay, so there's the whole computation from beginning to end. You can freeze frame that now. I guess that's a great thing about watching at home. You get to freeze frame. So any questions about that? Okie doke. Let's bring her home. All right, so let E be the field of order 512. Let beta be the primitive element of E, and let alpha equal beta the seventh. Oh, yeah, and let, all right, that's right. All you need to know is that the order of alpha is 73. Right. In fact, you can just sort of ignore all this stuff at the beginning, pretty much, and then get to the point where alpha to this that the order of alpha is 73, and which means that, oh, I should write this at the oh my gosh, I should begin everything by writing this. So remember that the length, yeah, the whole one of the whole points of what you do with BCH codes is that you want the length of the code to be the order of your sort of BCH elements, the sort of the finite field element they're using to generate this thing. And so yeah, so we're gonna figure out what happens to the BCH code where delta equals 5. The chosen desired minimum distance is 5. The actual one, who knows? But we want our minimum distance d to be at least delta, which is 5. So delta minus 1 is there's the other annoying -1 that shows up in chapter 7 and 8. You only want to go up, so that means you want to go up to m the minimum polynomial of alpha to the 4th. Yeah, so now we do the thing. This is a well-known computation. It's not easy, but it's a computation. So right, so we're going to express the generating polynomial expressed as a product of minimal polynomials. So O1, and now I'm going to use the abbreviated notation where I just write the powers 1, 2, 4, 8, 16, 32, 64. Oh, and actually, I said that we're going to let, once we get that the order of alpha is 73, we don't really need to know what anything else, but it is helpful to know that this is the field, the sort of initial field in which alpha sits is 2 to the 9th, so which means that the orbits are going to have size dividing 9, which means that if we get anything other than an orbit of size 9, something will have gone wrong. So there, I'm trying to cover my bases here. All right, so 128. Let me do that in green. 128 minus 73 is 55. Yeah, well, it's nothing like capturing an embarrassing arithmetic error on YouTube. So 55 doubled is 110. 110 minus 73 is 37. Yeah, well, that was number 8. So this is number 9. This better be good. 37, and 37 times 2 is 74, and indeed 74 minus 73 is 1. Great. And so we did in fact get an orbit of size 9. And then and the only other so the other orbit that we need to compute is the orbit as O3. So that's 3, 6, 12, 24, 48, 96 minus 73. And being, yeah, we got 20 minutes. I can afford to be careful. Oops, 96 minus 73 is 23. So 48, and then, oops, and 23, 46, and then we got doubles to 92 is 19. 19, 38, here we go.
and
then that's going to do it. I mean, and that's the ninth thing in the orbit, which is comforting. But just to be on the safe side, 76, 38 doubles to 76 minus 73 is 3. And we're back to the beginning. Okay, great. So find the generating polynomial g of x. So all we really in some sense to get this answer. I mean, you have to show the work, but once you get the work, then the only real answer to part A is that g of x equals m1 times m3. That's the answer to part A. So that's expressing the generating polynomial as a product of minimal polynomials. But then the thing you really need to know is that the degree of g is in fact 18. 9 and 9. So then part B, find the dimension of C. B, K, which is the dimension of our code, is going to be n minus the degree of g, which is 73. Oops. 73 minus 18, which is 55. Yeah, no problem, huh? Well, so this is C just is a 73. So length 73, dimension 55, D code, where D is at least 5 and probably is 5. Okay, so that's it. That's it, friends. That's the name of that tune. There it is, suitable for freeze framing or staring at it or whatever. Questions?
I had a general question. Just
Sure.
so like in a lot of the problems, it says like explain your answer, and then you didn't really explain in words on like when you were filling it out. So like how deep of an explanation do you want from us on the exam?
I'm going to give the worst possible answer, which is that it depends. But let me. But that's a good question. So well, okay. Let's look at. I think going through the 3 or 4 examples of explanation should give you a sufficient idea.
Or like
So
number 5?
yeah, it's just sort of q minus 1.
Oh,
So yeah, I mean the explanation is really sort of show your work here.
okay.
Oh yeah, that's how I use this. Can I do that with my finger? Oh yes, but very slowly. Oh my goodness, look at that. Yeah, so that's your explanation there.
Okay.
Uh,
If we like, and then also for like number 4, like that one also says briefly. So like if we just say like by textbook definition, or should we write down the textbook definition that we're using to like answer the question?
um, well, I think right. So the instructions actually say. I think the instructions. Nobody reads the instructions, but it is there. Unless otherwise stated, you may take as given anything that has been proven in class, in the homework, or in the reading. So you know it's given that the orders, these are the possible orders of elements, and so you know if it's not one of those orders, that's got to be one of the others.
Okay.
I mean, it's a very short proof, but this is actually a proof
Okay.
in its own way.
Cool.
Yeah,
Thanks.
welcome. That was a very good question. Uh, yeah, I mean the explanations are very short. They're like uh, like one sentence each maybe, but they really are explanations. I mean, you want to demonstrate that you understand the theorem. You want to demonstrate that you know that you understand and can apply the theorem, the relevant theorem, for each kind of theory-ish problem. So yeah, I know that's still kind of vague, but I hope that helps a little. All right, any other questions? Okay, I'm going to stop the recording